Morning, Orion. All right. We are getting closer to the end of the semester, and practically this is the last topic on modern control. After that, we will move to more optional material, which is related to developments of control systems in 80s, 90s, which is more robust control. So I will talk a little bit about robust control later. In my opinion, this is much more interesting topic for development and for application because it has all kind of cool, interesting theorems. No, you love theorems, right? So there you have a lot of unexpected stuff, magic stuff, which is like when you think about that, it seems to be impossible to do. And all of the robust control is built on theories which, on the first sight, look completely impossible. For example, you have things like, can you identify where all of the roots of particular polynomial without knowing the polynomial and having uncertainty in the polynomial? That sounds like impossible task. Even like if you're taking second order polynomial, it's already difficult. Let's say I'm telling you, well, you have quadratic polynomial, right? And in that quadratic polynomial, the first coefficient is changing in particular interval, second coefficient is changing in particular interval, and could be anywhere, like continuous interval, like from 5 to 78, whatever. Like, can you tell me that this polynomial family, which is all possible combinations of all of the coefficients, is stable? Sounds like impossible thing to do, right? Like you have infinite number of possibilities here. You get some generic polynomial, right? With all kind of coefficients that could have all kind of combinations of coefficients in particular intervals and ranges. And then I'm asking you, can you tell me that all of the roots of all of the possible polynomials from that family having roots on the left, for example, like in left semiplane? How do you do that? It seems to be like completely impossible because you need to test it. I mean, yeah, you can test maybe in some particular intervals, right? You can make some grid and test all of the coefficients on the grid, but who told you that you haven't missed that between the points part, right? You can miss point in between. It sounds very difficult, but actually the ideas behind that are very interesting and easy and applicable to other domains as well. And the point of what I want to show you also, not like to teach you robust control, it's entire course or maybe even two, but just to show you those kind of gems of thinking processes where you can learn something new and also see how it could be applicable to other areas, okay? This is the idea for future parts of that course, but today we'll talk about linear quadratic Gaussian control, which is, again, the last topic on modern control. And practically, I mentioned previous time that this is blending LQR with Kalman in a way, but we will tackle that problem for continuous time systems now, which will be a little bit modified version of Kalman filter, right? Any questions on the previous lectures or homeworks? Okay. So here are the things that we will be talking about today. Very short lecture because all of the materials for that lecture we actually learned in LQR. So you know all of the formulas, all of the computations, everything you need to know for LQG, which is linear quadratic Gaussian control, you already know. So practically I'm just skipping through all the steps and telling you what you need to do to compute it. All right, and then you will see some exercises on that. So practically speaking, this is optimal linear observer for continuous time systems is called Kalman-Busse filter. All right, developed by Kalman and I assume his student Richard Busse. And it's not different from connecting regular observer to regular controller in state space, which means if you're looking on the diagram here, you have some system with inputs U, outputs Y, and then you have maybe some reference or maybe not. And then you are modeling that entire thing given matrices A, B, C, sometimes even D. Okay, and then you have some observer here, which is connecting the output Y, estimated output Y and real output y. So you have error here. This error is multiplied by gain L, which is Kalman filter gain. And then you're returning it back to the system. And this system actually controls LQR controller, which is regular vector of numbers, K, right? So same thing we did, exactly the same thing we did with regular controllers and observers. Okay, same diagram. Just this K will be optimal K and this L will be optimal L. That's it. This is the difference. And I will show you how to compute that optimal L in Kalman filter, Kalman-Busse filter. And you know already how to compute that K, which is LQR. And this will be that LQG, right? So this will allow us also to handle all the uncertainties, assuming that the noise is Gaussian, disturbances are Gaussian. And this continuous time case. All right, so linear quadratic Gaussian control is just, as I said, adding these two together. And in block diagram, it will look like that. So in a sense, you'll have now two inputs to your actual plant. One input will be some disturbance or noise. If you remember, we multiplied GW, which was added to the system. And you can think about that W as additional input of noise or disturbance, okay? So this will be the disturbance input. And this U will be just output of your regulator, which is LQR in that case. But this regulator needs to read the input of the plant somehow from inside, okay? And also error, which means it needs to know what's the error between output and predicted output, and it needs to know the U part, which is control effort of the system, because this is what observers do, okay? And I want to write that, in that case, as transfer function also, okay? So instead of writing that as just K and L vectors, I want the actual transfer function of the controller to get it back to the form that I'm used to see in controls one type of courses, okay? So you have, for example, plant which is given by transfer function. I want to find another transfer function, which is feedback loop of some kind, and to close the loop with a transfer function on. And LQG control will be typically transfer function of some kind, closed loop transfer function and the controller transfer function. This is what I want to find. So how I need to think about that? This is how I think about that. This is input to the plant, which is control effort of the plant, right? And this might be some sort of transfer function. But I can take that input and return it back to Kalman filter, because what any observer or Kalman filter needs, it needs input and output, right? To correct for it, to compute the state. So observer, you can think about that as two inputs, one output system. In general, any observer, not only Kalman filter. So you're getting input and output as inputs to your systems input and output as input to your Kalman filter or any observer, and the output will be estimated state, right? This is how it works in general. So this is exactly what it says here. So you have Kalman filter, which gets input from here, and it's also producing that same input, by the way, that LQG thing. But you can also put it back into Kalman filter, because that's what you need. And also you put in error. You can include that maybe even in the box if you want to. So you have that error of the output, input. This is input for my Kalman filter. This produces estimated state as any observer. This estimated state is multiplied by K. And since I want negative return, which is negative feedback, I'm multiplying that by -1. And then I'm returning it back as U. So here I have already U for zero reference input. Okay, so I'm assuming a regulation problem, not tracking problem. So this is how it will look like in closed loop. But think about that as transfer function from that line to that line. So you can think you have single input, single output, practically speaking, between that Y bar to U. So you can think about all of that block as particular transfer function. And this is what we want to find. What is the transfer function? Which includes Kalman filter and LQR as a block, as transfer function from error to input, control effort. This is our goal. This is where we are going to say. By that connection, We know that we will improve performance of the system, so we'll handle low control effort because we are weighting that with R matrix or rho, right? So we can reduce the control effort. We can converge all of the axes as fast as possible to the correct axis and then to minimize the energy of the axis, which means they all will go to zero as fast as possible, optimally in LQR, right? And also it will be robust to noise and disturbances because we are using Kalman filter. In a way, Kalman filter is just low pass filter of some kind. So it kind of cleans some noises in the system in real time as it goes. Okay, so it estimates noises and cleans them, ignores them, because producing the mean possible value, most likely value, highest likelihood value for your output, okay, for estimated X. So we also heard about separation principle for observers and controllers, that we can completely separately design observers and controllers. They do not affect each other. We proved that theorem for observers and controllers of any kind. So in particular, obviously the same theorem is true for any optimal observers and controllers. Okay, you have same kind of principle. So given your system in that kind of form, which is AX plus BU plus GW, which is a part of uncertainty of your system or disturbance, and given CX plus DU, you don't have to use D, but since I'm not proving anything anymore, I can give you full formulas for the entire thing with D. Okay, so you'll have the entire thing. Same formulas work for regular observer and regular controller. Okay, you'll have same formulas. I just typically ignore D because I needed to do computations on that and calculations. So I assume D equals to zero, but you don't have to. These are the full formulas for observer, right? And this is what actually Kalman developed in the first place. So you can use also that generic J to minimize for your LQR, okay? It can have n equals to zero, okay? So you can ignore that middle part and to get standard way of X transpose QX plus U transpose RU criteria to minimize, but you can use any generic criteria because it doesn't matter, just like QR, okay? We saw multiple other things. You can add here like exponential part. Remember, you want settling time at least some behind some particular number, like faster than particular settling time. So you can add here exponent and other things that you use to. The point is that it doesn't matter what kind of criteria you're using, just use that criteria and compute your LQR completely separately from Kalman and design that controller, and you will get controller gain K. Okay, so you'll have that vector. And then you design Kalman filter using the tools that I will be showing in a second. Okay, Kalman Busse filter. And you will get matrix or vector L, depends on dimensions of your system, obviously. Okay, now you will use a standard control effort with estimated X, and then X estimated dot will be that Kalman equation, which is again same as observer equation, same Leuenberger observer and Kalman filter, same equation. Okay, it's AX estimated plus BU plus L times Y minus error. This is not Y minus error. This is L times error. This is entire thing is error, okay, of the output of the system. Okay. So here are the state equations when I'm putting that thing in. So I'm saying U equals minus KX estimated, right? And I get then that type of equations. Same kind of things that we've got for observer. Okay, same equations for that U. And from that equation in closed loop, because this is closed loop equation now, still linear. But now you have that one as input, in a sense, that Y bar. So in that case, closed loop transfer function will be that thing, which is the transfer function that we are looking for. The thing that you need to put attention to is that this is connected with plus, not with minus, as in typical control one type of systems, right? So it's kind of positive feedback, but it's not really because you have minus here. So I'm including that minus thing inside the controller. So that thing, that minus will be here, okay? This is a minus here that you have in closed loop. right? It's just more convenient for notation, in a sense. Any questions so far? So here's how you actually develop this Kalman-Busse filter. Nothing new. Take your formulas for LQR as they are, follow the Riccati equations and controller and equations like K equals whatever it was, B, K, R inverse or something, whatever the formula is for K. Now you call it L instead of K. All right, this is new name because this is for Kalman observer gain. All right, so LQR variables will be like that. So it will be A, B, C, D, S, Q, R, K. These are the variables that we used for LQR. So these are matrices A, B of the system, original system. This was S matrix, Gramian, if you remember, which was a Riccati equation variable that we needed to find from Riccati equation. Remember that matrix, n by n matrix, which needs to be positive definite solution of the Riccati equation. Okay, and then we wrote K as a function of that S. Now you have also Q and R matrices, which are variance, covariance matrices for the states and for the input, right? It's like regular weight matrices that you need to decide when you design your LQR. So these are standard names of the matrices. Now, to design observer, we have duality problem, and this is also one of the key ideas, I think, of that course, duality. So you can solve completely different problem using tools from another problem. And they have same solution because you can convert one formulation into another formulation. And it's extremely important in optimization theory, especially, where sometimes dual problems are million times easier than the original problems. And many times when you're learning on optimization theory, what people tell you, oh, let's solve dual problem instead of solving the direct problem. Because dual problem is much, much, much easier in terms of formulation and in terms of solution. So if you go and learn about that, especially for machine learning and other topics of that kind, you will see a lot of that type of approach, where instead of solving one problem, you're solving another problem, but then you converting that problem into your original problem somehow and connecting to solutions. Okay, so typically I'm giving some very simplistic example of that, but here's very like basic simplistic example of what duality might mean in terms of optimization and other theories in general. Let's say your problem is to name all the objects in this room. Okay, kind of difficult problem because you need like to think about like all possible objects that you can visualize here around you. Okay, and these objects also can change and so on. But let's say you have simpler problem. Name all the objects which are not tables. It's still super complicated problem because you still need to name million of different objects which could be found in this room. Okay, but dual problem will be name all the objects which are table. So saying here are the tables, this table, this table, this table. So you can actually show all these tables. And you're saying my original problem is everything else, which is not table, right? So you name practically all of them by saying this is what not table is. So this problem becomes kind of easier, right? Because now you need only to name tables and everything else is your solution to your problem. So this dual problem of naming tables is easier. But technically it solves your original problem as well, okay? As a side product, in a way. Because you needed to name everything which is not table. And this will be more difficult. So this is the same kind of duality where we solve the problem, now we want to use it somehow. So the solution is very simple. As with any observer duality, you have A converted into A transpose, B converted into C transpose. S, we convert, just give it another name. We still can use S, it doesn't matter really. In reality, it doesn't matter, just I can name that matrix any way I want, I just don't want to mix it with the previous S. And since we are computing both of them in the same exercise, I just want to separate them and give it separate name. So I'm using the same matrix that we used in Lyapunov equation, P matrix, covariance matrix. And then Q replaced with GWG transpose, R replaced with variance V, and K will be replaced with L transpose, which is the gain that we are computing. But originally it was row, now we need column. Okay, that's it. This is the difference that we are making. Everything else, standard equations that you have in LQR. Okay, same Riccati equations. Any questions on that? And last thing, you have also formulas for computing optimal J for continuous time and discrete time. Depends on what you want to compute. You just compute those sophisticated matrices, whatever they are, and you get optimal J. All right, this is optimizing J, but you probably will not even use it. Any questions on the theoretical part? Okay. So let's go to practical part and try to solve something very simple and very difficult at the same time because a lot of writing, but relatively simple. So close this thing. Okay, so what I will attempt to do is to solve LQR and Kalman analytically for the first order system, which is parametric system with given parameters, which means generic enough to be interesting, right? This is the idea. So I want first order system, which will be scalar system. Works. Okay. So my system will be very simple like that. The system will be x dot equals ax plus, let's synchronous and that, plus u plus w. And y equals cx plus v. For generic a, c, v numbers in that case. Okay. Is it clear what I'm saying here? This is one by one. All the things are scalars. That's 1 times u, which will be, practically speaking, v equals 1, g equals 1, and so on. But these are just generic numbers, whatever they are. Could be positive, negative. What do you think about stability of that system? Will the system be stable in open loop? A and B, but what is the condition for that thing to be stable? This continuous time system, obviously, so all of the eigenvalues need to be in the left semiplane. So what is the condition that all of the eigenvalues, first of all, how many eigenvalues you have here? Only one. So what is the condition on that one? Like, name it. A. So A needs to be negative for that to be stable. Okay, so A is your eigenvalue. Okay, that thing is the eigenvalue of that system. If A is negative, then the system is converging to 0 as exponent of AT. Okay, this is how it works. So the system would be stable for negative A, and it will be unstable for positive A or equal to 0. It will oscillate. Okay, that's what we know about that type of systems. All right, now we want to design LQG controller for this first part. We want to design LQG controller to minimize the J from 0 to infinity. And let's say we have something generic qx squared plus u squared dt. And Q and rho will be some constants, positive, obviously. So again, this is very generic LQR type of equations that we want to minimize. These two unknown parameters. Technically speaking, I can use only one of them. Why is that? Why I don't have to have two parameters here? I can use only one and get exactly equivalent solution. Can you think why I don't need that Q, rho, why I can skip them and get exactly the same solution? Assuming that none of them is zero, both of them are positive. You can write the same thing like that. You can define that thing as your new rho and kill that completely. Would that solution be different from that solution? Because you are computing minimum of that or minimum of that. Like, will minimum of that thing be different from that minimum? No, it doesn't matter. If you multiply any function by a constant, the minimum will not change. The location of the minimum. Okay, the value of the minimum will change, but the location of the minimum, you have some sort of function, okay, whatever that function is, and I have all kind of minimum points in that function. If you multiply that function by 500 or whatever, any number, but positive number, okay, not negative number, because negative number will flip it upside down, right, and scale. But positive number will just scale the function. So the locations of minimum will not change and still have same minimum points, right, same locations. No matter by which number you multiply, you just scaling it up like that, stretching it up or down. Same thing here. It doesn't matter by which number, positive number, I multiply the integral. They can multiply it by any number. 5, 10, 25, doesn't matter. I'm just minimizing based on that part. And this part is still some positive number, right? So I can call it rho tilde. Nothing changed. So I don't really need two numbers. I can use one, but I will use two just to make it generic enough. Okay. Okay, so we also know that this noise is normal with zero mean and variance V. And this one is distributed as normal noise, zero mean, and variance W. Okay. Again, generic numbers. We will solve it all generic, okay, for all these variables. Any questions so far? Now we'll design LQR part and Kalman part, Kalman-Busse part. So here's the LQR equation that we need to solve. So LQR equation would be A transpose S plus SA plus Q minus S B R inverse B transpose S matrix 0. In that case, it's not matrix, it's scalar 0. All right, so let's put together all of these things. So A transpose is A. I don't need transpose anymore because it's a scalar. Transpose of scalar is scalar itself, obviously. Okay. S is just scalar S in that case. Plus SA, so it will be twice SA, practically speaking. Plus Q, because our Q in that case is this one. You can think about it as X transpose qx, right? Which in that case equals x qx or qx squared. Since scalars we can move left and right if we want, it's not a problem. So this is that thing. So our q is that thing minus s. B in our case is 1. It's nothing. R in our case is rho inverse. B again 1, S equals to 0. So this is what we have. We have twice SA plus Q minus S squared divided by rho equals to 0. Now I can multiply both sides by rho, since rho is positive, so it's not a problem. Just over here, it's Q rho Q. Okay, this is quadratic equation. I also can change signs, that will be more convenient. That will be minus here, plus here, minus here. And then I have two solutions. So S, solving quadratic equation, will be 2a rho plus square root of 4a squared rho squared plus 4q rho, all of that divided by 2. Do I need to choose plus or minus? Here. Or both? What is the condition on S for LQR to be nice behaving? So what need to be the S? So you have two options, right? You have two rules for quadratic equation. One is plus, one is minus. So which one should I choose? Plus or minus? Why plus? So S should be positive definitely. What does it mean for scalars? Positive definitely. It just needs to be positive. That's what it means for scalars. Okay. So to make that positive, what do you choose, plus or minus? So all of these numbers are positive and all of these numbers are positive. A might be actually negative. So this number actually might be negative. But even so, this number will be bigger than this number because it's the same number squared here, right? And plus something positive. So this will be bigger than that thing in absolute value. So this will be more positive than this part, the absolute value of this part. Which means if you choose plus, it still will be positive. But if you choose minus, probably not. Okay, so we are choosing plus, not minus. Now, could you imagine that minus also will be positive? It will work. In that case, you have unique solution to LQR. It cannot be. Okay, if your system is controllable, okay, it cannot be. And this is clear even from that equation. Again, absolute value of that part is larger than absolute value of this part. So if you put here minus, it's definitely something smaller than this one. So subtracting from smaller value, bigger value, you will get something negative, for sure. Okay, no matter what values you pick for all these variables, doesn't matter. All right, so we picked our S, and then all we need to do is to write that S A a row plus square root a squared row squared plus 2 row. And just dividing by 2 here. So canceling Z2, canceling Z4, and canceling Z4. Okay, practically speaking, these are canceled. And you get that, this plus. And K, using the formula for LQR, is R inverse B transpose S. P equals to 1, R equals to rho. So you have practically S divided by rho. This is the solution to your optimal controller. You'll have S divided by rho, which is just A plus square root of A squared plus 2 divided by rho. Okay, pay attention when I'm dividing that thing by rho cancels here, rho squared cancel inside of that thing, and then you need to divide that thing by rho squared. So it will be Q divided by rho, like that. So this is your optimal LQR controller, right? Any questions so far? Okay, now we need to design carbon filter. As I said, we will do that in parallel to that thing, just replacing names of the matrices with different names. A will become A transpose will become A, B to C transpose, C to B transpose. Same equation. So here's the equation. You'll have, and S will be replaced with P. Okay, so it will be AP. So I'm replacing A transpose with A, S with P, plus P A transpose. Q is replaced G W G transpose minus P C transpose V inverse instead of R inverse CP equals 0. This is our new Riccati equation for that case, for carbon. Now we will put it in. So we'll have AP plus PA plus G in our case equals 1, right? So it will be W minus P C will be just regular C squared, and P will be P squared, all of that divided by 0. Since these are not matrices, we can do regular manipulations, scalars. Okay, now this is also quadratic equation in terms of P, right, which we need to solve. So this is what you'll get. You'll have C squared P squared minus twice A B P minus BW equals 0. So I'm just multiplying by V all of that thing, combining these two together is twice AP. Okay, we get the quadratic equation. Now I need to find P. So P will be solution of quadratic equation 2AB plus or minus square root 4A squared B squared plus 4C squared UV divided by 2C squared. Form of a quadratic equation solution. And again, if you're looking on that part, which could be positive or negative, obviously, and looking on that part, these things are positive, right? Because this is something squared times 4 times something positive. So this thing is added to that thing. but square root of that thing is this thing, which means that absolute value of that thing is definitely bigger than this thing. So you cannot use minus here. Same idea. To make this thing positive, you need positive definite. In that case, just positive. You have to use plus. So let's see what happens. The solution will be a divided by c plus square root a divided by c squared plus w divided by v. Okay. That's the right thing. So that's the same thing. So we can cancel 2, 2, and 4 here. Okay. I'll get AB plus square root a squared plus c squared w v divided by c squared. And the gain will be, again, using the same formula, but now we are inverting everything, so it will be all transposed. Okay, so the transposed part will be P, C transpose, the inverse. If you remember, when you transpose the entire equation, all of the matrices change in the order into opposite order. Right? So you get that kind of thing. So this C transpose will be just C, V inverse will be just divided by V, and that equation will be, after some algebra, A divided by C plus square root A divided by C squared plus W divided by V. So this is our Kalman gain.
Is it C transpose or C?
C transpose is C. This is scaling, so it doesn't matter. In that case, this is C transpose in the formula. This is like generic formula, right? But in our case, this is just C. Any questions so far? So we designed LQG controller. So this is first part. Any questions so far? All right, now we can move to the second part, understanding of what we actually got. Okay, question number 2. What happens when rho goes to infinity? Look at the formula there. You can copy it maybe. It will be easier to work here. So our gain was optimal was a plus square root a squared plus q divided by rho. So what happens to that formula when rho goes to infinity? So where this thing goes? No. No. Actually, depends. Could be. So this is A. So when rho goes to infinity, limit of that thing. So this is Q divided by something huge. Right? So it's 0. This part is 0. So you get the thing A plus square root of A squared. It's not 2A. This is the same. It's not 2A. This is A plus absolute value of A. So if A is positive, then it's 2A. But if A is negative, then this is 0. Depends. Okay, the square root of something squared is absolute value of that thing. It's defined as something positive. Okay, so if A is stable, then you get A equals 0. If A is unstable, the system is unstable, K equals 2A. Does it make sense? So why does it make sense? What is the intuition behind it? What does it mean that rho goes to infinity? Remember, this is like J, you have to minimize J, where you have control effort versus states. So you're optimizing output versus input energy. So if rho is huge, are you minimizing energy of the input or of the output? If rho is huge. Because rho multiplies input, right? You have integral of y squared plus rho u squared, something like that. So if rho is huge, will u be small or y? X, whatever. What will be small if rho is huge? You're minimizing that thing. So you will penalize energy of the input. Because you'll say, if u is larger than 0, this thing will be huge compared to this thing. So I want this thing to be as minimal as possible, right? To make it balanced somehow, okay, to minimize that thing. So if I'm going with that up, u will go down, energy of u will go down, okay, by minimization process. So I'm penalizing on high control effort. So what does it mean? I don't want any input to my system. I want input almost 0. Not rho goes to infinity. That's what it means. But what does it mean to have k equal to 0? U equals minus kx. Right? This is how it is defined. Which means if k equals to 0, u equals to 0. This is exactly what you want based on that condition. So it makes sense that you would get k equals to 0 because you don't want to invest any energy in any effort to control the system, okay? So if it is stable in open loop, which means it converges by itself somehow to zeros from initial conditions, whatever they are, just keep it going. Don't give it any input. Give it input 0, practically speaking, okay? So your controller will automatically produce 0 input to your system. Nothing. Don't touch it. Let it converge by itself. That way you will not be able to invest any energy in the system, right? You will not need to invest any energy in the system. So it automatically will happen by that type of controller. But what happens if you have opposite situation where system is unstable? So if you are not investing any energy in the system will just diverge, right? That's what will happen. It's unstable. So what should you do? Remember what was the solution provided by symmetrical root locus? What should you do to invest like minimal energy when you have to stabilize it, just to stabilize it? Like, just make it stable, don't touch anything else. What was the solution of symmetrical root locus to that? But rho goes to infinity actually. Because this is the point where it starts. So where is the position of your eigenvalue for that case? Then you have, let's say your symmetrical root locus, your open loop is like that. This is your open loop. So how your symmetrical root locus would look like? It will be mirror image. So it will jump here, just a mirror image. And this will be your optimal one. which means whatever the poles, unstable poles here, you will just reflect them here, and then they are your rho goes to infinity answer. Let's see if this is what happens here to that thing. So what are the eigenvalues of that thing? That Si minus A plus Bk. This is what it is. This is location of closed loop poles, optimal ones in that LQR. So where they are? So it's S times 1, so this is scalar. So it's that S minus A. What is B? One plus 1 plus 2A. Not plus, multiplied by 2A. What is that? That S minus A plus 2A. The determinant of scale is the scale itself. Okay. So it's just S plus A. Minus A plus 2A is A. Right? Logical. This is exactly what it says. So your root was at positive A. Your optimal root at negative A in closed loop for rho goes to infinity. This is what you expect from theorem of symmetrical root locus. This is exactly where it is. Okay, so let's try some other condition here. Other question. Now we have, for example, W goes to 0. And then the formula that we are looking at is the development of L. So what happens to L when this happens? It's A divided by C plus square root of A divided by C squared plus W divided by V. So what would be your observer gain, optimal observer gain or Kalman gain when W goes to 0? Same thing. Okay. Again, you have two cases. You have case where A and C are of the same sign or of different sign. Okay, so if they are of the same sign, which means positive, positive, negative, negative, then they add up together. So we'll have, so option 1 will be A divided by C times 2. It's option 1. They have the same sign, right? If they're of different sign, what do you get? Then you get 0. Okay. Different sign. Okay, so what happens, for example, if A is negative? C is positive, which means the system is stable. Okay, so what Kalman gain would be? It would be 0, right? Based on that, does it make sense that Kalman gain is 0 when W goes to 0? What does it mean W goes to 0? Intuitively, like your variance of your system disturbance or uncertainty is going to 0. which means you're extremely certain about your system. And it is stable, and it is converging, obviously. Which means just throw out your measurements, ignore it completely. This is what this thing is saying. Like Kalman filter 0 means your error from your measurement is just your measurement noise, because your system is precise, exact. Okay, your system is producing exact values for your development. Okay, you believe it 100%. Completely ignore the output. You don't care about measurements. Measurements are noisy. They don't care. So when W goes to 0, you say, practically speaking, that your model is perfect. You don't need any measurements. You know where the x's are, just based on the model. Okay, which is obviously not realistic, but this is the assumption here. Okay, and then Kalman gain will be just 0. Just multiply error by 0 and don't use that error. Just use your model as is, ideal model. This is a condition, right? Now, it's interesting that when A is unstable, this is not the answer, right? Because you need to be very careful what happens when A is unstable. But the trickiest part here is when A is unstable and C is negative. This is tricky part to interpret, like why you still cannot use your model anymore. This is more deep question. Think about that. Okay, let's try some other conditions here. Let's say, here's the next one. W is much larger than V. Okay. So this one is much larger than this one. And these ones are approximately of the same kind of order of magnitude. So A and C are not exactly super different. But W is much, much larger than what happens to A. This means that uncertainty in the model is much higher than uncertainty in the measurement, practically speaking. Okay, so the measurement is okay, your sensor is good, but your model is not great. What happens to that? So what is that limit? So first of all, just look at that very simply. I mean, I don't even need to compute that limit officially. Okay, so this is W divided by V, when W divided by V is much larger than 1. This is completely equivalent. Right? So if V much larger than W, then W divided by V is much larger than 1. So it's like huge number. All right? So huge number plus some number. Okay, you can ignore that number compared to that number, right? And then this also some not huge number, but square root of huge number is still huge number. So huge number plus small number is that huge number, approximately. Okay, this is how you think about limits in general, okay, after calculus course, because they would kill you in calculus course if you would say something like that in one of the tests, right? But now in engineering, we can approximate things. So practically speaking, this is the only thing which is left here when you add in that to that thing. And then you have that thing going to square root of W divided by V, because everything else could be ignored compared to that ratio. When you add in something to that ratio or square root of that ratio. All right. So this is how it will be. And you will have pretty huge gain in your Kalman. Is it reasonable? Does it make sense? It makes sense because you want to penalize on huge error or potential error in Y. Your model is uncertain, right? So you do not trust your model. You have pretty horrible prediction of where your state is. After you have that prediction, You're saying now I have measurement, which is pretty good. Okay, but error is still huge. I need to change my state significantly, right? So the states need to change a lot from my present states because the error is huge, but measurement is good. So you need huge gain for that case. All right. Any questions on that? All right. That's it for today. Thank you.